Welcome to qnawire.
So here in this problem there are two parts of the equation, and in the A part we have to find the rate of energy loss by the hot pizza when it floats in the outer space. And to solve this question we have to take our own values. We can take any value that we want to take. So let us take that the radius of pizza is 30 centimeter and the thickness of the pizza we can take as 2 centimeter, and let the temperature of the pizza be 100 degrees Celsius. Now we can find the energy loss, and we know that the pizza is in outer space, so there will be no conduction, no convection, only a radiation mode of transfer of energy will be there. So the formula for a radiation heat transfer rate is given by P is equals to sigma epsilon area times area T to the power 4, and we can take the emissivity of pizza to be 0.80. You can take any value. I am taking as 0.80. Now first of all we have to calculate the area. So area of the pizza will be equals to 2 pi r square plus 2 pi rt is the total surface area. So it will now, we're going to plug all the values here. So 2 pi r here is 30 centimeter, but we have to take it into meters, so it will be equal to 0.3 meter. Now we can plug the value here. 0.3 meter whole square plus 2 pi r here is 0.3 times t. Again t we have to take in meters, so it will be 0.02 meter. So 0.02 meter. Now we're going to simplify and we'll get the result as 0.60 meter square. So this is the area of the pizza. Now we can plug all the values here. We know that sigma is a constant whose value is 5.67 into 10 to the power minus 8 watt per meter square degree Celsius. Now we can plug all the values. So P is equals to 5.67 into 10 to the power minus 8 watt per meter degree Celsius. Its unit is wrong actually. It's watt per meter square Kelvin to the power 4. So meter square Kelvin to the power 4 times epsilon is that is the emissivity, that is 0.8, times area is we have calculated 0.60 meter square, times temperature we have taken it as 100 degrees Celsius, so if you have to convert into Kelvin we'll get 373 Kelvin. So 373 Kelvin to the power 4. Now we're going to simplify and we'll get the result approximately 530 watt. So this is the energy loss from the pizza per second. This was the answer for the A part. Next, in the B part, we have to find the rate of temperature change. So to find the rate of temperature change, we know that the internal rate of internal energy will be equals to the rate of energy loss by the pizza. That means we can write one equation to solve this question, that mc delta t divided by dt is equals to P. This is the rate of change in internal energy and it will be equals to the rate of energy loss. First of all we have to calculate the mass of the pizza that we don't know. For that we have to take the density of the we have to assume some density for the pizza. So let us assume that the density be 500 kg per meter cube, and again we have to assume the specific heat of pizza also. So we can take it as a 3000 joule per kg degree Celsius. So first of all we'll calculate the mass. So the mass of the pizza is nothing but the product of density of the pizza and the volume. Density we have assumed to be as 500 kg per meter cube. Now the density, now the volume will be equal, the volume of the pizza will be pi r square t. So we can plug the values here. So pi r here is 0.3 meter whole square times the thickness, it is 0.02 meter. So we're going to simplify and we'll get the mass of pizza to be as 2.8 kg. So this is the mass. Now we can plug all the value in this formula to calculate the rate of temperature change. So from here we can write that the delta T divided by dt is equals to P divided by MC. So P we have calculated as 530. It's joule per second. What can be written as joule per second? Divided by mass is 2.8 kg times the specific heat. Specific heat we assume to be as 3000 joule per kg degree Celsius. So we're going to simplify and we'll get the result as 0.063 degrees Celsius per second. So this is the rate of change in temperature that we have calculated to be 0.063. You can take degree Celsius per second also and Kelvin per second also, because when you take a change, the Kelvin and the degree is same. So it's degree per second. So this is the final answer.